We've all seen it happen. One student looks at a new problem and instantly sees the solution, while the student sitting right next to them looks at the exact same problem and hits an invisible wall. It's tempting to look at that difference and assume the first student simply has more raw intelligence. We often treat the human brain like a passive hard drive, assuming you either have enough storage space for new data or you don't. But learning is a dynamic process. To figure out why that second student got stuck, we have to look to educational psychology. This is the scientific discipline dedicated to opening the black box of human cognition to see exactly how we acquire knowledge. To trace the path of an idea, we have to start at the microscopic level, inside the biological mechanics of a single mind, and then expand outward into the broader social ecosystem where that mind operates. When you map that entire structure, a clear picture emerges. A student's struggle is rarely a lack of ability. It is usually a failure to align with the hidden psychological mechanics that govern how the brain actually functions. Let's start from the inside out. Long before a student interacts with a textbook, learning begins deep within the biological architecture of their own brain. Swiss psychologist Jean Piaget established that biological readiness dictates what a person can actually learn. You cannot expect a mind to grasp abstract logic if it hasn't physically developed the neural capacity to process it. Here on the left side of this graphic, we see Piaget's 4 stages of cognitive development. A child's mind builds itself up, progressing from basic sensory motor functions to the formal operational thought required for advanced problem solving. As outlined here, new data must be deliberately encoded, held in working memory, and stored long-term. If attention wavers, data is lost. This encoding is highly individual. Notice the right side detailing learning styles. Brains favor specific sensory pathways to lock information in: visual, auditory, kinesthetic. Sitting above all of this is the brain's highest internal function. This section illustrates metacognition, the mind's ability to step outside of itself, to actively plan, monitor, and evaluate its own progress during a task. When diagnosing why a student is struggling, the first step is checking this internal machinery. We have to verify if their brain is biologically ready for the material and actively processing the data in front of them. Functioning internal hardware isn't enough on its own. The mind operates within a reactive social sphere. Under the theory of constructivism, true knowledge is actively built, not passively received. That construction happens in the space between solitary struggle and guided assistance. This diagram illustrates the zone of proximal development. It highlights the critical threshold where a student is right on the edge of a breakthrough, but requires a teacher or a more knowledgeable peer to reach the next stage of understanding. Psychologist Albert Bandura expanded on this social necessity with his social learning theory. He found that the brain is hardwired to learn continuously by observing and imitating the behaviors of the people around us. Peer interactions directly forge a student's sense of self-efficacy. As this chart shows, positive social modeling leads to persistence and resilience, while poor modeling results in low self-efficacy, triggering avoidance behaviors and failure. Even the strongest cognitive abilities will stall out if the surrounding social sphere fails to provide the friction, the modeling, and the guided support necessary to pull that student forward. Finally, we must zoom out to the widest perspective, the macro environment of the physical classroom. This illustration outlines the core tenets of classroom management. Setting clear expectations is rarely about simple disciplinary control. It acts as an environmental shield required to protect these complex cognitive and social processes. When an ecosystem goes unmanaged, chaos takes over. Disruptions immediately trigger cognitive overload in a student's brain, interrupting working memory and shutting down both internal processing and healthy social interaction. Managing a classroom is about engineering a stable ecosystem. It creates a space where the psychology of learning is safe to operate. Learning is an intertwined loop. It relies on biological readiness, memory encoding, social modeling, and environmental stability, all working together. When a student hits a wall, we have to stop viewing it as a lack of ability and start treating it as a systemic breakdown in one of these distinct layers. By applying this scientific framework, we move past trial and error. We can finally align the conditions of the mind and the environment, ensuring that every student has the structural support they need to succeed.